Okay, before the break, we looked at a whole bunch of things about keys. There's more than just primary and foreign key. And we need to know those terms in order to look at the further forms of normalization. As far as this class, on the assignment, or the assignments you submit, I need to at least be able to tell you're trying to get to third normal. If something goes a little wrong, that's understandable, but if it looks like you didn't even try to get to 3.5, I will definitely say something. Or that will definitely be an issue. For those who've had me in class before, you know I'm much more likely to send you an email and ask you to correct it than just put a bad grade on it until we run out of time at the end of the semester. If it's anything more than just a couple of points here and there. And if it obviously is so far away from third normal form that I think you didn't even try to go to 3.5, I will definitely be saying something. So we have more normal forms after that. The next one is elementary key normal form. Or EKNF for the acronym, which seems like something some people try to pronounce. So maybe think about that, especially if you're getting into that analytics and how you pronounce that word, that acronym, because you may sometimes hear people try to say something like EKNF or put some sort of pronunciation to that. And this is, there's a super key functional dependency. Is it okay if I write FD for functional dependency? So FD is functional dependency. I'll put a note over here. Functional dependency, which is rather large, 2 large words that are going to show up in every single thing that gets written on the board today. So I'm going to write that as FD. And I'm going to include the dots because we don't normally use the acronym for that. We do say, if we shorten it, we just say dependency, and then the functional dependency is implied. But since I'm writing things out on the board, I'm going to put the dots there, so hopefully indicate that it's not necessarily a standard acronym. So a super key foreign dependency, or I should add something to the beginning. Each attribute, so each attribute in our table has a super key foreign dependency or is a prime attribute. And prime attribute means it doesn't show up anywhere else in the entire database. There's nothing else. That's the one and only one spot you're going to get it from the entire database. So we can't improve storage if it's only stored once and never shows up anywhere else. Kind of a mouthful again, so some clarification points. Well, that red marker doesn't work. Bless you. Let me try this red marker. Oh, that seems much darker. So not just the primary key, like in 3NF. Each attribute has super key functional dependency, or it is a unique prime attribute to that table. Otherwise, this is really a special case of 3NF. I'll even write that on here. special case of 3NF. So third normal form was like this, except it said that each attribute has a functional dependency of the primary key or is a prime attribute itself. Here it's the super key, and notice the elementary key is in there, so it doesn't have to be the whole super key. Third normal form, it has to connect to that whole super key, which eventually got minimized down to a candidate key and then labeled as the primary key. If we have that functional dependency, it'll be in third normal form. But if it's only to one or two fields from the super key, just part of the super key, then it's elementary key normal form. So big technical words, but hopefully you see they fall right from the definition of what an elementary key is. Because the next one's not so nice as far as names. Voice cod normal form. Or BCNF, which for some reason this one did like the mathematics thing where they gave it a person's name. There's actually a large movement in mathematics to try to stop that and rename all of those theories that have people's names because it's not useful at all, right? Nobody really cares who came up with the idea. This one, the name explicitly, the definition falls straight from the definitions that show up in the name. But whenever it's named after a person, that doesn't happen. We have to like memorize it separately. Mathematics is traditionally very, very bad about that. All the big math theorems have a person's name, and it doesn't help you at all to figure out what that theorem does. But one of the normal forms ended up that way for some reason. And it's kind of a step further, super key functional dependence only. So another special case of 3NF. Actually, I'm going to write a special case of the elementary key normal form. Special case of elementary key normal form. So we lose that prime attribute requirement. So we don't have any brand new data in our table, but everything depends on that one key. So that's like the bridge tables you all put together. I would have put something about, I was just complaining about that name thing. I'm actually a math person, and that's a big deal in math. There's all those confusing things. Did I spell that wrong? Oh yes, there's an E, B-O-Y-C-E, God. I was complaining about that. I would have done something with bridge, because that's our bridge tables. Like y'all, like just fell out of y'all naturally last week after we talked about bridge tables the first time. It's like, okay, we end up with a bunch of many-to-many relationships. We shouldn't have any many-to-many relationships, so let's take a table in the middle and break those down, so then we go many to one and then one to many on the other side of that bridge. So everything in the table is dependent on that super key only. The things tying them together. Notice we've kind of broken away from primary key as well. Up to 3NF, it had to be the primary key specifically. But now, if we have a key, any key, so we can modify it to the particular situations too. It's not necessarily an overall thing for the database. 3NF is primary keys 1, 2, and 3, primary keys only. So that affects the entire database. Afterwards, we're going to be talking about super keys every time. So we can find unique situations inside of our database to fit our current task, not just the overall thing. I'm going to put that on there. Bridge tables, think bridge tables. Bridge tables would not be the only place to sit that this shows up, but that's a good thing to think about to make sense of what that technical definition of super key functional dependence only means. That's kind of a mouthful with 1, 2, 3, 4 words in that definition, and 3 of them are probably new to you this week, right? So think about the bridge tables, where we have to adjust our relationships, so we add an extra table that is made entirely of keys from somewhere else in the database. We're not storing any data itself in that table. It's just a connecting thing. Now we get back to numbers. Fourth normal form. Yeah, and again, there's a huge movement in mathematics to do away with this. The whole individual name, and that's going to flow over. So if that moves forward successfully, that'll carry into any computer science terms where theorems are named after people as well. There's not a group that decides that mathematically, right? Things just pick up the name along the way. If anybody would decide that mathematically, it'd be the Lucretian chair. Stephen Hawking was the last one. There hasn't been another one selected after him. So there's not somebody that would make that decision right now. As far as, okay, all these theorems need to be named, and then the math's going to carry over into computer science. So this one, it might be worth expecting to change, right? Not next week, but if you're heading into data analytics now, 15 years from now, you might hire some students fresh out of college, and they use a different term for that. Just that's why I brought that up. It's something we can see happening in the future. But moving back to a nice name, fourth normal form, obviously the next step, because these are special cases of 3NF. This is a special case of 3NF, and this is a special case of the special case of 3NF. So we haven't got to the next step yet. The fourth normal form is any multi-valued dependency includes a special key. Kind of hard to make sense of it. Like, okay, that's a lot of big words. It definitely sounds like something that would be a technical definition. Let's look at our example here. So multi-valued dependency, we want to come query this table we made. And we say, how many people live in Indiana? So we look here, we look at the state field, and just count those. 1, 2, 3, 4. We got 4 people in our database table that came from Indiana. But does that depend on any other fields? It doesn't depend on any of the things that were our super key candidates, right? Let alone our candidate key or the primary key we selected from, I guess, the one option we listed as a candidate key. That one kind of by default has the label. But the state doesn't depend on anything. However, other things would. For instance, how many people have the last name Person? Person. Or maybe a better question is, what are the first names of folks with the last name Person in this database? So here, but we need multi-values. By the nature of that question, the last name's implied, but we'll still count it. So there's 2 there. 2 there, so there's 2 there. So there's 3 people in our database that all have that same name. And that does depend on the primary key, because There's George person, and George person. So all three people with that same last name, those multiple values we're looking for do have to be separated by unique identification afterwards. We do have to go back to our super key to tell that that's not just duplicated data, those are three different people. In our case, from that one we selected, those are the number fields and the address. The entire super key would be needed in order to identify that that's not just a repeat in the database. Those are actually different people. So those fields, first and last name, depend on the rest of the super key. That's what that's saying in very technical terms. Obviously, when you take multiple choice quizzes, like in a class or certification exam, you're going to see those technical definitions. So I'm going to make sure that makes sense. What's next? Essential tuple normal form. E, T, and F. Nothing surprising about the acronym. Has everybody heard the word tuple before? I've heard it in a programming class, but as far as math class, do you know what the word tuple means? If you've gotten up to sixth grade math, you've used tuples, just probably didn't thought the word for it. A tuple is a multi-valued collection. So, for example, XY. Everybody's had algebra class. We worked with XY points. The point requires two values, so it's a tuple. Same with XYZ. Red, green, blue. They go together. Three values that we always put together in the same order. Ordered multi-valued collection. Otherwise, it would be a set. So take a set and put a strict order on it that doesn't change. So a mathematical term you may not have heard, but you would have worked with those since at least sixth grade. And sixth grade is the point that we pretty much guarantee everybody has seen the tuple. You just probably hadn't heard the words. So every join must be a super key. So we can no longer make any arbitrary connections. When we do our diagrams, the diagrams pretty much always show up that way. Right? When we do our ERD diagrams, the relationship we draw on there, which is the join. Join is a keyword when we do the query. That's where join means we're going to pull from more than one source. Could be more than one table. For us in this class, it's more than one table. Could be more than one database. That'd be data warehousing. It could basically be anywhere that's data lakes. We pull from lots of databases, lots of flat files, lots of social media posts, and we pull from everything. To get to the extreme end of it. For us in this class, a join means we're going to pull from more than one table at once. But every time we do that, it must be a super key. That's how our diagrams always look, but that's not necessarily how our SQL code looks when we go to run that. Maybe we have names, we have the standard integer primary keys, and that's what our diagram shows connecting it. But when we go to write our query, we know that a name and age is going to be enough. So we don't even pay any attention to the key. So technically we could draw another relationship between those tables based off the ones we need, Not just that one that, well, for y'all's case, not just the one that you expect me to be expecting on the homework. The one the teacher, your teacher is expecting when they grade the homework. The other stuff we can use to connect our database. There's lots of it in there if we start looking. Lots of ways to join it. They don't show up in our diagrams, but when it's actually applied in the database, that only that thing that we always put in the diagram, the primary to foreign key relationships, are the only connection left. That's essential tuple normal form. Because every collection we draw, everything we pull from that table is essential. It's not an arbitrary connection between the tables that we just happen to notice was there and could save a couple fields in our query. It is the actual connection between them that we labeled in the diagram. There's a nice little phrase to put this in English, because again, this is the technical terminology you're going to see on a multiple choice quiz. But there's a common way to put this in English, which is the combination of primary key and foreign key is unique for the whole database. Combination of PK and FK, the primary key and foreign key, is unique for entire database. So I'm going to write database, but then I'm going to come back and write out and kind of half cross that off and write data source. Because some of y'all will be progressing down data analytics pathways and eventually get to data warehouse and lakes, where that's still that same concept still applies. So whatever you're pulling from, but for our case here in this class, we have one database with lots of tables, and we don't have the same primary key, foreign key combination at any two spots. Every relation is unique. And yeah, for your writing assignment, you're basically going to list these out like I'm doing here, list out what it is and write a sentence. For 1, 2, and 3, you need to write the steps out, because those are the ones that are required for all your homework assignments. Try to get to their normal form. But for the other 7, there's 10 in total, all the way up to 6 NF. Just list them out and write a sentence. Try to put it in your own words. Try to make sense of that big technical term. It's okay if I erase this? I think I asked already. Fifth normal form. Every join is made of only superkeys. That sounds an awful lot like the one we just put a definition up for, right? There are some distinct words, and these are very technical definitions. Every join must be a superkey. I guess we could put the word has there. Every join must have a superkey. Doesn't really change the meaning of that. Over here, every join is made of only superkeys. So on this one, essential tuple, at least one side of that is a super. So we have a table over here, and maybe this column's our key. There's our super key, and I guess I could have done it like an ERD diagram. There's another table over here, and this super key ties in here. And the super key from this table is over in this column. So our relationship is here, maybe one too many or something. However it goes, but it goes from super key to just normal field in this table. And then our super key over in this table is over here. But for the fifth normal form, we have that super key in the table somewhere. And then over here, I'll do a two-part super key, SK1 and SK2. So maybe we need a bigger super key over here. Whatever this table's storing, there wasn't, if we just bring this over as a foreign key, it's not quite enough to tie them together. But that relationship does go from one super key to another. The difference there is that now that field tying them together is part of the super key over here. It helps you uniquely identify each record. It's a little addendum here. I don't know if those pictures were helpful. I'm going to erase the little pictures. But essential tuple, we just need a super key on one side. And fifth normal form, we need the super key on both sides. And that's what I was saying a moment ago. That's how our diagrams all look, right? Very first ERD diagram y'all did without being told to do that, everybody in the class did that automatically. But that's not the only relationship we have between those tables. We could find more if we looked, if we started digging around. So when you start restricting and constraining your database, that's going to be the keyword used. Your database is constrained so that the only relationship between any two tables is that thing that shows up in our diagram. We can't go digging around and find extra ones. Then it's fifth normal form, which I think I was putting asterisk C's in green. So it must be implied by the candidate keys. The last week's homework has an example of this. There were two little situations to work on. One of them was the students, the courses, and to tie those together nicely, everybody put in that third table in the middle, right? The enrollment that brought in course ID and student ID. Those keys that uniquely identify the records in our other tables very much implied that those were to bring things together. It was obvious before you even drew the third table in there that those keys were created to make the third table. The second thing in the homework, not so much. So there was orders, right? We had customers and orders and shipping information. But we also had, was it vendors, suppliers, something like that? We had another table. And obviously to make our database functional so that we can ask for things, I think it was vendors from the vendors table and things from the customers table at the same time, we need a relationship. Maybe tie into a bridge table. Maybe make up another field itself just to put in there. But we need a relationship between them, but it's not as obviously, the relationship isn't as obvious as it was with the student ID and the course ID. When you look at those, very obvious that the reason for those is to make that bridge table. But when we have customers and orders, bridge those together, it's kind of obvious. But where does the vendor fit in and the shipping? How does the vendor and shipping fit in? because the vendors, like the supplier, right? That's the Chinese wholesaler that makes it. The database itself is the middleman that imports it and then sells it to the final consumer. And then the shipping is going to be just around America somewhere, right? FedEx or UPS or something like that. So it's not as obvious. The primary keys don't immediately imply how they're going to be related. So sometimes we have to force them in there. Also, one more example of why we see student databases show up so often in examples, because they just naturally fit in. They fit so nicely into the database examples. Oh, there's a blue marker. What's next? Domain key normal form. So, I'll just write down the definition. So every constraint, right, that was our keyword when we moved on diagrams. We haven't seen a whole lot of SQL. Generated some SQL. I can look at this stack. That's still open? Yes. So when we set up our primary key, we constrain that to be the primary key. And if you have a composite key, comma separate the values. But to create our primary key, we constrain it. We created the field up here. We create the field, and then later we constrain that key to be a primary key. And when we set up the relationship, we constrain that primary to foreign key relationship, tying the tables together. So constrain are those restrictions we put on the forms the structure of our database. So every constraint must be a logical consequence of the definitions of domain and key. Every constraint must be a logical consequence of domain and key. So everybody heard the word domain in math class before? It is the domain from math class usage of domain. So back in math class, you might have seen something like, well, it probably as a function. F of x equals 2x plus 3. Nice little line. And they'd ask the question, what's the domain of this function? And that's asking, what numbers is it okay to plug in there? What are the allowed inputs? In this case, any number is fine. Maybe another example in math class, and they ask g of x is 29 over x plus 3. What numbers are allowed? In math class, we always start with the assumption we can do everything and then roll out the things we can't do. Most people only get up to 3 cases of things you can't do. College algebra will, at the very last lecture in college algebra, we'll have the 3rd thing you can't do. So it's a much shorter list of things we can't do, and we can't divide by 0. So we know that if we plugged in a -3, that would work. That would cause problems. So we're not allowed to plug in that one value. So it pulls out of the domain. So that's what's meant by domain here as well. What are the allowed input values? For a example like what we've seen, maybe our type, I'll go with the MySQL instead of the Oracle one. We have a decimal number. It's 5 digits long. 3 of them come after the decimal point. We saw that in data types, right? If you're in Oracle, it'd be number 5.3. There's a couple variances on that, but from that data type, there's a lot of things we're allowed to plug in there. But what about pi? Can we put pi in that? When we're in a hurry, the numbers we put in, we just quickly punch in our calculator, we'd probably be okay. But pi is a constant. Computers have very special cases of pi built in. There's a website where we can go download pi to 1 trillion digits. Go download 1 trillion digits of pi. If you haven't seen that before, as far as your program, when you're programming that, that counts as a string, and then every next digit gets the value gets calculated. The value of that column gets calculated from a string, and we just store it. But 1 trillion digits of pi, and there's still an infinite number more digits of pi, right? So pi would not be in the domain of that data. So what are the allowed inputs for that? We have an integer data. 23 would be fine. But that would not be in the domain. A string would not fit in that domain. The domain is the allowed inputs. What's allowed? If we have text input, the number 23 wouldn't work. We need quote marks around it to make it the word 23. Oh, fit in text data. So every part of our key has some sort of domain that goes in to build up that super key, and eventually we end up with that collection of domains that we're allowed, the values that are allowed to plug in as our super key. We also have the definition of key. We went over a whole bunch of definitions earlier, right? Key is the unique identifier, and then whatever one we're working on, it has to fall naturally out of that. There's a really nice, put this in English. So there are no more, there are no, because I needed a unique ID column, right? That primary key integer, because I needed a unique ID columns. I'm going to put the translation in English like that. That quick and easy thing that we're going to do over and over again, pretty much everything we do in this class, that unique ID is an integer, primary key, auto increment it, and then we know we have a unique field. But we made that up just because we needed a unique field. When there are no more of those left, we only have the data we naturally want to store. There's no extra data. Everything just falls from what it means to be the domain of our database. The data we want to store somehow works itself into being a key. This is where we no longer have the degradation performance on the computer side. Right, we talked about that earlier. There's a slight degradation in performance, but really the reason you see it noted over and over and over again is because of human performance. So there's nothing we can do technologically about it. We're asking humans to do harder things, so it's going to take longer. At human timescales, because humans are doing it, not a machine. AI might solve that problem, but data analysts are the ones that build AI models, so they're not really in a hurry to replace themselves. But AI might solve that problem. But for now, there's the human thing, and these are still complex queries. We have that, but it's easier at this point. It's still complex queries, but we don't have as much human degradation as we did back here on ETNF or even 5NF. That performance degradation is gone by this point, but it's a lot of work to get to that point. So very rarely does this one make the cut. Do we take it that, do people take a database that far? Unless there's really, really good reason to do so. But by the time we get there, we no longer have the performance degradation. And then all of the normalization is worth it, except for all of the steps of normalization we had to go through to get there. That bridge table I just talked about a moment ago, the course IDs and the student IDs kind of fit that. The IDs were made up for that situation, right? For those tables when y'all were putting those together last week's homework, you were just thinking integer to uniquely identify the student and another integer to uniquely identify the course, just like the numbers you see on your schedule, right? On your course schedule from school. But if we got rid of those numbers and then found another way to uniquely identify every student, there's going to be something in there we can uniquely identify them from. Like our example earlier today, the name and address and several fields put together can cause a unique thing. If we do that instead of all the ID numbers, then that bridge table would be an example of this. The domain key, and that just, all of our relationships fall naturally from the data we're storing. There's nothing extra put in there just to make it enough, just to create nice relationships. It's okay if I erase this one or this side. And 6 normal form. Only trivial joins. So we have it in domain key normal form, which is all the obvious stuff that naturally falls out of our data set. Clean that up so that it's everything there basically counts as trivial. Which that means no bridge tables. Keep going a step, if you go full normalization, this is fully normalized. That's the highest level. We clean it up a little bit more every step, right? That first thing we do before we even throw out the word normalization is throw in those bridge tables to get rid of any many relationships. And we start cleaning it up. Eventually we get down to domain key, normal form, and we get rid of those integers we made up just to have a unique record and look for the super keys that would naturally fall in there. Filter those down so they're a little smaller to get candidate keys, label one of those as primary keys in every table. And then we come back and clean up those bridge tables we threw in at the very beginning. Get rid of those bridge tables and find other relationships between the naturally occurring candidate keys. And then we're in 6 normal form. That is fully optimized. That is as good as it is theoretically possible to get as far as storing our data set. Which also happens to improve our write times. So we get improved write times, and we pass DK and F, so we're back. We no longer lose that performance thing, but still, if somebody asks you about normalization, you're going to talk about performance degradation because we almost never go this far. It's a lot of work to get here, and then we have to take a big step to get here, and then we go back to step 1. Then we go back and clean up what we did at step 1. So it is a lot of work to get here. There has to be a really, really, really good reason to do that. But this is the theoretical version. Theoretically as good as it gets. I looked at this right before class. So the Wikipedia page is up to date. So when you're working on that writing assignment, it if you search for database normalization and hit the Wikipedia page, they have a really nice chart here too. So you can see every layer we add one extra step. And sometimes you might see this almost identical chart, except there'd be a green check mark here. These are very, very similar. Some people call it 6 normal form if we still use those unique primary key IDs like we're going to do in this class over and over again, the easy ones. The auto increment integer, we're going to keep those around because it's just so much work to get from here to here. If we skip this step and we still have all those auto increment integers here, a lot of people will just clean that up and call it 6 normal form. So it's very, very, you will see this chart written both ways with that one, that obvious X that seems out of place where it's generally considered optional and we can call it 6 normal form. But a nice little chart, you'll see a new level is added every step along the way. If you look up at the top here, well, we talked about this in the history section. The idea of relational database is 1970. He wrote it down, started working it, started talking about it, spread it around. And as other people talk about it, they very quickly realized some ways to clean it up. They were trying to promote it, so lots of people were talking about it. It was the hot topic in computer science. As you can see from 1970 to 71, that was definitely the hot topic in computer science. We got all the way to 3rd normal form by 1971, which was years before anybody started using relational databases, if you remember back to the history section. The essential tuple form wasn't created until 2012. So up until 2011, there was still a 2-step process there. But now it's we start with a, Wikipedia says unnormalized. We usually say denormalized, like we undid it for some reason, but it's much more common to say denormalized than unnormalized. I guess unnormalized makes more sense as far as the prefix, but denormalized is easier to say, I suppose. But we start with the denormalized database, and then each form we add one further step along the way. So you can think of it as all of the previous one. The next one requires you to already be in the previous normalization. With this exception down here, and if you wouldn't have to look at very many different sites before you found one that had that with a green check mark instead of a red X like Wikipedia is, because that one's debatable. But for that writing assignment, list out this first 3, 1NF, 2NF, and 3NF, and details the step by step how you're going to do that. Right, you're going to write a paragraph on each one of those, talking about how you get something in 1st normal form, and the rest of them is a short list. Just fill out the name of it, write a sentence, cover the definition, try to put it in your own words as good as you can. The very technical definitions, because for some of the people in the class, this will be the only time you ever hear that. And when you write that essay, that way one time you those into data analytics, it'll show up more often, but I kept pending that today. It'll show up as far as putting the debate together on whether it's worth it. We talked about the steps, what you have to do each time to clean it up, very briefly. So knowing what those steps are, and then as you understand the processes more as you do your data analytics program pathway, you'll know what to do to get in that form. So most of the rest of what you're going to hear about it, data analyst, is going to be on the debate of when it's worth it or not. When it's worth the work, all the work to put it in that form. And as far as software developers, you may never hear those words again. So please include them in the writing assignment, because this might be the only time you ever see those words if you're an SF major. And when we asked about that at the beginning of the class, everybody in here is either heading towards data analytics or software development. You're on one of those 2 pathways, but a long list, Hopefully that kind of made sense. Lots of technical jargon. The next few things we have to cover are going to be example based, so we get to go back and follow along examples and do stuff along the way. But the debate over whether it's worth it to do this, which is going to be unique every situation, is a lot more than the work. Because it's a lot of work for those times that it is worth it. So you want to be absolutely certain that it's going to be worth all the work you put into it. Because somebody's making really good money to do all that work too, right? So from the data analytics expert perspective, it's probably always worth it because they're going to get paid by the hour. It's going to take a lot of hours to get all the way to 6 normal forms. So obviously the person getting paid by the hour wants to put in those hours and get that paycheck. So it's you have to convince the person flipping the bill that it's worth it to go that far. And usually there's a stop somewhere. 3NF is kind of necessary because if you don't get the 3rd normal form, you lose the guarantee on cascade update, cascade delete, which means if you update your database, you have to go back to and confirm that every field was updated. Go back to your database field by field and update and confirm, which is not fun. So we always want to get that far. The other notes I have here. Oh. Does anybody have any questions about that? Okay, I assume 5 seconds of silence means no questions. If you have any, send them my way. I'm always happy to help. Otherwise, I will see you all on Tuesday on campus. It's the next on-campus required day, and it'll be a group work day that day. So a couple of announcements, very brief talking, and then you will actually be doing something the whole time instead of listening to technical definitions. See y'all Tuesday. Have a good one.